It started. Hello, everyone. Can you wait for some 10 or 15 minutes and then I will start the session. So anyone new to join? I'll be waiting for 10 or 15 minutes. Worst case, at like 5:15, I'll start the section. We're working on getting the tactics for anyone who is interested. Yes, I guess chat has started working now. I think it is coming back in the chat. If you guys need me to do anything else, then let me know in the chat. I can do it. Is the audio fine? maybe can you guys let me know if the audio is fine or if it's like breaking or something? Hello, hello everyone. Um, Let me know if my voice is clear now or if it's still breaking. It's low. If it's still low, I will do some additional settings. Just let me know. Yeah, so I'll start in like another 5 minutes. Okay, you guys want more mic volume? Okay, give me a minute. Okay, how about now? Is it better? Okay, nice. Yeah, I'll start the session hopefully by 7:15. Um, Before that, let me show. quick overview of what we will be going through. Once, yeah. So yeah, wait, sorry guys, can you hear me now? Hello, let me try to fix the volume. Hello, it's breaking again. Okay, give me 1 minute. I will fix it. Hello, now can you guys hear me? Hello, you guys can let me know, please let me know. So that I can continue. What about now? Mainly sorry guys for the having some audio. So let me fix the audio first and I'll be right back. Hello. What about now? What about now? Hello.
So it's picking up all the background noise. I'm not hearing you. No, that's because I haven't enabled it, but you can see here how much background noise it's picking.
Yeah, hello. Can you do this, uh, one sec. Yeah, can you guys hear me now? If it's still breaking, give me a few moments. I'm sorry for the delay. I'll try to get it fixed. Is it better now, as in you guys can now actually listen, or is it still breaking, but it's just more audible? Hello, guys, can you hear me? I'll continue trying till 7:30. Let's hope that it gets fixed by then. Yeah, is the audio good now? Or is it still big? Hello, can someone just tell me in the chat quickly if the audio is still breaking or um, it's working now? Still breaking. Okay. Give me a few minutes, guys. Sorry for the delay. Be fine now. I doubt it's a network issue. Um, is it good now? Finally? Okay, nice. Is the audio fine? As in the volume? Is the volume fine? Okay, nice, nice. Okay. Um, so I think it's about time. Yeah, okay. Yeah, sorry for the delay, guys. Slide skill issue, but okay. So let's get started with the role of electronics. So, so I would say electronics, I mean robotics you can classify into three major parts, right? Mechanics, software, and electronics. So the mechanics part is um, like the actuators and like designing the structure of the robot itself. That's the mechanics part. The software part is like the core logic of the robot, like the brain of the robot, you can say. And then comes the electronics part. So the electronics part is all the sensors, the motors themselves, how to control the motors, and the software part actually runs on the hardware that the electronics part provides. So for basic stuff, it's microcontrollers. So the software runs on the microcontrollers, and we'll be looking more into the microcontrollers today, and then how to actually program them and use them today. So first, I'll introduce you guys to something called Tinkercad. So I did see from the poll that a good number of you did use um, Arduino and all before, but even I have been using it for a long time and I didn't know about the existence of this website. So Tinkercad is a website that you can log into and you can make these nice looking circuits and you can simulate these circuits. And by doing this, you have a few advantages, and I'll show you those. So the first one is that you can actually save your components. So this is a very simple example. So here I've just connected a LED via a resistor to the Arduino's 5 volt and ground. And now usually, at least when I was doing it, I used to just put a nice big resistance, but that need not be the case. Sometimes you may or may not mistake it and put a small resistance, in which case you will actually exceed the current limit for this resistor. And Tinkercad warns you about this. Here it says, the maximum current is supposed to be 20 milliamps, but you're providing 184 milliamps, right? So Tinkercad is useful in this way. So it's showing me that I will probably burn this LED if I connect it like this with this resistor, which by the way is 1 ohm. 1 ohm is way too less for this. Now, yeah, so in this one, this was like a very simple case, right? It's like very simple to spot that your resistance is very less. But in cases where you have much more complex circuits, it might be quite hard, and Tinkercad can help you identify, that this is drawing too much current or this might burn or something beforehand. So it's good in that way. The other way, oh yeah, and this is some memes I found. So Here is a rare case of where you're passing way too much current through a resistor and somehow it didn't burn yet. So it literally became a light emitting resistor. And this is what happens when you, let's say, burn a component. So you can see here the ash marks on the component. Um, but yeah, the second thing about Tinkercad that's useful is that it's very organized. You can see how organized this circuit is here, and you can see the same, not the same, but a similar circuit here, and you can see how like more cluttered it is, right? So Tinkercad can help in this way. Any questions as of yet? So to summarize, Tinkercad is helpful in two ways, majorly. One is to make your circuit look very nice so that you can visualize what you're doing beforehand before actually going to the hardware and actually putting all the connections. The second one is that it can help prevent shorts. So, okay, very nice. All clear, then good. Um, Now the basics of using development boards. So here is the Arduino Uno. This is an image of the regular Uno R3. And you can see how much stuff is on here. So this right here, this like I think yesterday it was described as a centipede looking thing. This right here is the Atmega, and this is the microcontroller. This is where all our logic and everything runs. This is the microcontroller, and this is where everything happens. Everything around it are accessories to make this microcontroller more easily accessible by us. So for example, this microcontroller has a lot of pins and you route all of these to these output pins. So these are all digital output pins, we call them. I'll tell more about this later. These are all analog output pins. And you can see here, this is a 5 volt output, this is a 3.3 volt output. This is the ground pins. So technically, all the dev board is doing is actually helping you interface with this microcontroller very easily. And it allows you to do this for a more wide range of stuff. Like with the same Arduino, you can probably do 100 or 150, many projects, interface it with many different sensors. So it's not specialized to a specific use case. And that's basically what a development board is. It allows you to use a microcontroller in a nice and easy way and in like a generalized fashion. So some other components here, you guys are not required like to know this, but I find it cool that there's so much just to use this one microcontroller nicely. So this is a barrel jack. So if you don't want to provide power through this USB connector, you'll use this. And speaking about that, the USB connector is what you connect. Like your laptop will have one end of the USB cable, and the other end will be connected to this port. Now, only via this connection, we are going to program the Arduino. And this TTL converter I'll get to later. These are just fuses. This is a 5 volt regulator. So in case your input is not a nice 5 volts, this will convert it to a nice 5 volts. One thing about microcontrollers is that they require a nice and stable, what is it? Like they require a nice and stable voltage input. So if your output, if your like voltage input to the Arduino or the microcontroller is not a nice and stable 5 volts, it can cause issues. And that's a 3.3 volt regulator. So see, here we are getting 5 volts, but we also have a 3.3 volt, right? So this converts that 5 volt to a 3.3 volt. And all of these are ICs, by the way. Like this is an IC, this is an IC, even this is technically an IC. And yeah, so, but the base point is the microcontroller is the actual brain, and the development board just allows us to interface with it in a very nice way. Apart from that, there is this thing I would like to point out. So if you look at this right here, this is something called an ICSP. It's basically another way to program the microcontroller. So I don't know if it was taken yesterday, but you can program microcontrollers using different methods. One of them is via this. So this will go via this converter, and then that will go, and then that will program the microcontroller. The other way is you connect these pins directly, and then you program it. So this is two ways to program the Arduino. Anyways, moving on. Um, so Arduino Uno is like a it's like a very good starting point. So the documentation, there's a lot of documentation online. It's a very good starting point for people who have not used the Arduino and stuff like that beforehand. So in case you are one of those people who have not used a development board before, I would suggest the Arduino is a very good starting point. It has a very nice community and it has a lot of good tutorials online as well. So you can probably get started from there. And yeah, this again. So when we want to program the Arduino, we will basically use this port and connect it. So there will be a connector, and we connect that to our laptop. So let's assume that this is a laptop. So we connect this to our laptop. Then we have something called an Arduino IDE. So in this IDE, we can write code or software. And then we program that onto the chip. So when you program something onto a chip, it's like once you program it, it's stored on the chip. So next time you don't actually need to power it like this. You can power it via the barrel jack. What I'm trying to say is like you can have like once you program something, we say that it's flashed on. So there is a flash chip here, and what that does is, or it's an internal flash, it holds the code that you send to it, and even after you power it off, it stays there. So the next time you power it on, by default, the Arduino starts executing the code that you had entered last time. And yeah, so in some projects, like if you want to put this on a robot, you don't really want a cable running to your laptop all the time. So what you do is you'd like by robot I mean like a car or something that moves. So you would program it and then you will connect the barrel jack so that it just runs on its own with power that's on the robot itself. So next slide. Yeah, okay. So every pin, so you can see here, there are a lot of pins here. These are all pins that we can use. Um, Yeah, so there are these pins which are digital I/O pins, and there are these pins which are analog input pins or analog I/O pins, whatever. These are analog. The distinction is these are analog and these are digital. I'll tell more about these in like 2 slides. But so these are all I/O pins, and specifically these digital I/O pins we can configure in a few ways. So the first method is an input. So let's say we have our Arduino and we want to connect it to something that's going to be giving us a reading. So let's say some very basic sensor is here. So we have the Arduino and then we're going to connect it to a sensor. And this sensor will give a digital output, right? So in that case, what we'll do is we'll connect this sensor to a digital port on the Arduino. And now we'll configure it to be an input. So the sensor will give an output, and the Arduino will take that data as an input. So usually when you have stuff like sensors, you configure the port it's connected to as an input port. And when you have stuff like servos or actuators or motors that you want to control, that case you'll use them as output. So input means the microcontroller will be reading the voltage or it will be getting an input, let's say, that's an analogy. And output means it will be writing the voltage or it will be giving the output. Okay. And there's this third case called an input pull-up. So this is kind of specific. So one use case of it would be, let's say you have a button. So what a button does is very simple. You have two wires on either side of the button. So one button is here. I mean, there's a button there. There's one wire there and there's one wire there. And when you press the button, it shorts these two wires. So it creates a link, right? So that's the button. But what happens when the button is actually not pressed? So if it is not pressed, then this short never happens. So both sides of the wire are technically disconnected. And what this leads to is something called floating voltages. Floating voltages are basically when the microcontroller doesn't know what voltage it's supposed to be reading. Like, as in the voltage will fluctuate, which is not something we want. So in those cases, we use these things called input pull-up or input pull-down resistors. So yeah, like you can see, this is the button. This is a button, okay? These two are buttons. And so what you do here, like you'll be connecting this to the IC's input pin, and instead of the ground here, you'll have like the sensor or like this is the button. So whatever the other side of the button is connected to. So what will happen here is that by default, when this button is not connected, you'll be reading 5 volts because like there's nothing to pull this down. There's a resistor here, but there's no current flowing. So this will simply read 5 volts. And similarly, when this is disconnected, this is connected to ground. There's no current flowing through. So this will basically be 0 volts. And so this will be reading 0 volts. So this is a pull-up resistor where it will default read plus 5. And this is a pull-down resistor where by default it will read, oh wait, no, my bad, is the exact inverse. Oh wait, no, I'm correct. So a pull-down resistor by default it will read 0 volts. Whereas a pull-up resistor by default it will read plus 5. Default as in when the button isn't pressed. Like a button is a specific use case, but it's the easiest one to understand, right? So any doubts till now? I feel like I'm going a bit fast. If you guys need me to slow down or go through something again, let me know. Oh, okay, fine. If it's fully clear, then it's good. Let's go on. So now I told about the IO pins, right? So there are these things called digital IO pins, and one sec. Yeah, okay. So there are these things called digital IO pins. So if we go back, yeah. So these right here. These are the digital I/O pins of the Arduino Uno. There are a total of 14 of them, and these two have very special uses. And you see these like these symbols here. This is like a tilde. If you zoom it in, it will look something like this. And this stands for something called PWM. I'll come back to this a bit later. But so this within these IO ports, there are these two which are a bit special. They're used for something called UART communication. That also I'll cover later in the session. Um, and there are these within the remaining ports. There are some ports which have a tilde symbol, which mean they support PWM. Which again I'll tell about later. But yeah, like I said, pins 0 and 1. So if you see here, pins 0 and 1 are used for UART communication. I'll tell that later. The pins with the tilde support PWM. And okay, and when I say these are digital pins, that means that when you configure them to an output, they will like only you can only write 5 volts or 0 volts and nothing in between. Obviously, I'm excluding PWM. PWM I'll get to a little bit later. Um, and if you put them as an input pin, you can only read the approximate voltage. So if it's 4 volts, then it will read logic high. And if it was 1 volt, it will read logic low. So there is like a distinction that happens. So if it's, I think, I don't know the exact values. These are like completely approximate. But if the voltage is lesser than 2.3 volts, then it's logic low. Again, this is all approximate. Point is like it's not 2.5 greater, it's high, 2.5 lesser, it's low. There is a in between range where it's completely like you don't know what logic it is. But let's say if it's lesser than 2.3, then it's logic low. If it's greater than 2.7, then it's logic high. So point being, you can't read like the in between voltages here. Like if the pin is getting like a 3 volt input, it will assume that that is logic high, and it will all you can read in the software is logic high. You can't read anything else. So that's about digital I/O pins. Next is the analog input pins. So see, you can configure them as an output pin, but let's say so there's something called a DAC and a ADC. So a DAC is a digital analog converter, and an ADC is a analog to digital converter. The Arduino has these. So when you get an analog voltage as input, so in this case, you can get those that and you can convert it to digital signals for the microcontroller to read. But when you have a digital signal, the Arduino doesn't have these, by the way. So this is a digital to analog converter. So you cannot convert digital pins to a analog voltage. So when you get that's why these pins are labeled as analog in. So yeah, see, the analog in is because these have ADCs. So you can convert the analog voltage into a digital method that the Arduino can read. But when you're going to write outputs, right? So when you want to write an analog output, like I think many of you would have heard about the dimmable LED. So that is a very popular example that's used. So in that case, you'll use these tilde pins. These pins with the tilde here, like look here, 9, 10, and 11, 6, 5, 3. All of these pins, they support PWM. So since the Arduino doesn't have the DAC, you would have to do something called PWM to get these analog signals. So what you do is you have, let's say this is 0 volts right here. And let's say that this is 5 volts right here. But I want to output 2.5 volts. So instead of outputting, let me say green is the actual 2.5, right? Green is the actual 2.5. Rather than outputting that, what these pins do is that they alternate between 0 volts and 5 volts with a 50% duty cycle. A 50% duty cycle basically means that half of the wave they're at low and half of the wave they're at high. So now if you see, if you take this as a wave, I don't know how I'm going to highlight that. Okay, let's say this is the wave. Right? This is the wave, let's say. So now for half of this time, it's at 5 volts, and the other half, it's at 0 volts. And so since all waves are just like a repetition of this, if you do the math, you're basically doing 5 volts times T by 2 plus 0 times T by 2 by T, right? So what this average comes out to is 2.5 volts, which is the voltage we want. But it's not a true analog voltage. It is okay. PWM is known as like if you expand it, it's pulse modulated width or something like that. But point being, basically by changing this duty cycle, you can arrive at different analog values. So let's say you want to get I don't know 3 volts as the analog output. Like you want to write 3 volts to a pin, then you will make a pulse width of, yeah, pulse width modulation. Yeah, my bad. So you will make this to be, I think, 60%, and then so when it's high, so this is 5 volts, and then this is ground, 0 volts. So yeah, I think will you make it to be 60%? Uh, yeah, so this will be 60% of the periodic wave, and then ground will be the 40%, and then it will recur like this. So by doing this, you're creating like pseudo analog voltages, let's say. But yeah, these aren't true analog voltages. They are pseudo analog voltages. Also, this the A0, A1 pins. So um, like the digital pins. Here we had these two which are dedicated for UART. There are these two pins as well, which are used for something called as I2C communication. I'll talk about this also later. But yeah, so you can, these two are also kind of dedicated for I2C, but that's only if you decide to use them. If you don't decide to, you can use them as normal analog input pins as well. Okay, now that we're done with that, let me make a quick blinking LED in Tinkercad. So I wanted to show you guys just how nice this website is. I think you guys should try it. So once you log in, you'll get a page like this, and you go here to this create button, and you can create a circuit. Now, once that's done, you'll get to a screen like this. So this is a project name, and here are a bunch of components that you can use. These aren't even all of them. This is the number of components that you can use. So this has a variety, like some of the ICs. If you want, you can try. This is a 555 timer. You can try make a clock with that, clock signal with that. And there's a bunch of other really cool ICs here. But I want to just stick to the basics, and I will use an Arduino. So here, this is the Arduino in Tinkercad, and you can have an LED and a resistor. So point is to make a simple blinking LED code. And by doing this example, I hope any of you who don't know how to code an Arduino, you will learn that as well. So the anode we can connect to some pin here. I'll just take pin number 9. or why not? Pin number 10 also I'll take. The pin doesn't really matter. We'll configure that. Um, and then here you'll connect the cathode and then you'll connect that to ground, right? So the circuit is basically this. All you're doing is a LED, a resistor, and then that's going back to ground. Now to actually code the Arduino, you click on the component and then you click on code. So this is a block kind of way of coding. It's for people who are not introduced to C yet. And I'd say this will be somewhat intuitive. You can try this as well. But I will be using the text mode for this. So when you're coding the Arduino, there are these two loops that you start with. There's something called a setup loop, and there's something called there's a setup function, sorry, and there's a loop function. So setup function is what will run the moment you connect your Arduino and then you program it. So the moment your program starts running, this will run exactly once. So this function will run only once and at the start of the program. Okay. Now this loop function, the moment this setup function is done, all the microprocessor, I mean the microcontroller will do is loop through this function again and again and again. So once it's done with this, it'll again come back here. So it will be stuck in this infinite loop. And all of your logic and everything will go here. And here you'll do the setups, like right here. So here, this is like a default code that Tinkercad provides for blinking the built-in LED. I will remove that and I will start from scratch. So let me just remove this. Yeah. So I always like defining the pins I'm using here. So here I'm using pin number 10 to drive this LED. And here I am going to be writing voltage here to this pin. I am writing voltage. So I will configure that pin as an output. So first let me define it. LED pin is 10. Also, I'm assuming you guys know like the basics of C. And int is a data type, and this semicolon is required at the end of every line. This is the assignment operator, and this is the name of the variable. I'm hoping that most of you know this. Don't worry about attendance. I will get to that soon. There is an attendance slide. I will get to that soon. It'll be there in this meet itself. Anyway, so I'm hoping you guys know the basics of C, like the semicolon is there. The code we're writing is mainly C with a bunch of custom functions, let's say. So one of those is pin mode. So pin mode, like I said before, you can configure all of these pins to be one of like three things: input, output, and input pull-up. So you can configure this to be any of those. So the way to do that is you write pin mode and then the pin. So here I'm going to be doing that for LED pin, and I'll be configuring it to be an output, right? So this is that. So all this line does is basically tells the microprocessor, we are the ones who will be writing a voltage to this. You don't need to read from it. We will be writing voltage to this. And the reason we're doing that is because once we write a voltage to this, it will go here and then there'll be a current. We can configure this resistor. By default, it's 1 kilo ohm. And then you go back to ground. So that creates a completed circuit and the LED will glow. Now to actually make the LED glow, we will use something called digital write. Okay. I spelled that wrong. Yeah. So digital write is a function which basically writes either a high or a low voltage. High voltage being plus 5 volts, low voltage being 0 volts. So it will write that voltage to the pin that we select. So here we do LED pin and we do high. So my point being, now this line, what it will do when it's executed, it will make this voltage high. Now when we want to blink it, we want it to be high for some time. Then we want this to be low for some time. So the LED will glow for some time. Then when this is written to low or this is connected to ground, it will turn off. For that, we need to delay for some time, right? So there is a delay function. And here, the number you're entering is the time delay in milliseconds. So I will delay for 1000 milliseconds, which is just 1 second, right? And now you can just copy this code. And instead of writing it to be high, you can write this to be low, right? So let's go through this once again. I'm defining which pin I'm going to use. So I'm using the 10th pin. So that's LED pin is defined to be 10. I'm using pin mode to define that this is going to be an output pin. Then I'm writing a voltage. First, I'm writing a high voltage. So it will write this to be high. This will become plus 5 volts. Current will flow. This will glow. Then it waits for a 1 full second. Then after that second is over, it will write this pin to be low again. So now this is ground and this is also ground. So there's no voltage flow. So the LED won't glow. And then it will delay another 1 second before it goes to high. So then you click start simulation here, right? And as you can see, it's a blinking LED. Okay. So that's the this is the most basic thing that you can do with an Arduino. Um, we will later go on to using sensors and stuff. It will still be very basic, but with the Arduino, you can do a bunch of stuff. Usually, this is the first thing any beginner does. So, any questions, guys, that you guys have on this? Okay. If there are no questions, then let us get back. Yeah. Okay. Now, now that the blinking LED is done, um, let us go to a quick question. Okay, this is something I wanted to show. Um, but yeah. So, like I mentioned before, Tinkercad can show when a component is going to be fried. But you can see both of these circuits are doing basically the same thing. They're making an LED glow. But in one case, it's showing that the LED is the one that's frying. And then in the other case, it's showing that the Arduino itself is what is going to be broken. So the difference is basically that here you're using this a pin that the microcontroller controls to power this LED. And in this case, when the resistor is too small, it causes too much current to like flow via the microcontroller, and thus this will the microcontroller will what be the microcontroller is what actually has the excess current flow. In this case, the 5 volt isn't actually like these power rails aren't routed via the microcontroller. They are routed via, like I told, that's a 5 volt regulator, right? This is the 5 volt regulator. So the output from this is what goes to this. So, having too less voltage, I mean, too much current drawn here will only damage this. It won't really damage this, right? So that's why here it's saying this is the LED is what will fry, and here it's saying that the microcontroller is what will fry. But yeah, that's a interesting distinction between the two. Okay, now we get into no, I believe the 3.3 is here, if I'm not wrong. Yeah, see, this is the 5 volt regulator. There's another 3.3. You're not wrong, but that's here. The 5 volt is actually here. Anyway, so now to get readings from sensors. Um, okay, so let's start using readings from sensors. So okay, so there are two sensors that I will be showing you guys. The first one is an IR sensor. You can get it in a module like this, and the other one is an ultrasonic sensor. You can get it in a module like this. I don't have the IR sensor with me, but I'll try to show a demo of the ultrasonic sensor working. Now, let's get started. So the way an IR sensor works, I like to know how the sensors work internally. So I'll tell you guys about that right now. So IR sensors, basically they send an infrared signal. So these are signals, infrared wave. So these are waves that we cannot see by ourselves. but it basically goes and then it hits a surface, and then based on what color the surface is or the type of the surface, some or like most of the wave may not be transmitted back. So one of these is a transmitter, IR transmitter, the other one is a receiver. So based on how much of like the wave that it transmitted it receives, it can determine what type or what color the surface is. So specifically, dark surfaces they absorb a lot of the infrared, and because of this, most of the infrared that it transmits, it doesn't receive it back. And based on that, there's this potentiometer here. Uh, for anyone who doesn't know, a potentiometer is basically something where if we turn this screw, let's say it's a screw, if we turn the screw, then we can change how much resistance that has. So by turning this, we can change how much resistance it is, and internally it is configured so that this changing this resistance will change how sensitive it is. So by modifying this resistance, we can basically adjust the sensitivity of the sensor. Okay. So where will this sensor be used? You can use it for line following robots. So here you have a black color line in basically what is a white colored background. So these sensors can easily, once they're like properly calibrated. So to calibrate, you again change this. But once they're calibrated, you can easily find the distinction between what is a black line and what isn't. And because of that, they are widely used in these line following robots. Um, yeah. So this is basically what I just told. Um, Yeah, and also this is a digital output. So it doesn't really tell us how much of the wave it's receiving. It filters that out and it only gives us a digital output. So based on how we calibrate this, it will either give us a high or a low. It'll only give us digital outputs, is the point. So this is a circuit that you'll use. So you're providing it 5 volts and ground for it to function. And then the output, you're connecting it to a digital pin, right? Um, and yeah, that's about it. So wiring is very, very simple. And yeah, you have to configure this pin, the pin number 9 on the Arduino. You have to configure it as an input pin because this is what is giving the output. So the flow of the signal will be from here along the wire and then into the Arduino. So you want to accept the volt, or like you want to input the voltages that it's giving. So you'll configure it as an input pin. Um, yeah, anyway, so yeah, you could connect it to an analog pin and it'll still work, just that it'll probably read 0 or 5 volts. So that's the only difference. Anyway, so now connecting this alone won't be enough. You'll have to actually code it. So you'll have to code the Arduino to understand that, oh, I want to read the values that it's given. So how you'll do that is this. So you'll get like I said, the pin that you're connecting is pin number 9, right? Pin number 9 you're using. It's behind all of this. But yeah, you're connecting this to pin number 9. And so you write a variable, which is a constant. A constant is basically something that won't change throughout the duration of the program. And this pin, you're not going to change it in the middle of while it's running. So it's a constant. And that's configured to be pin number 9. Then this is something called a serial. I'll tell about this in a little bit. And then there's this. You're configuring this to be an input because we discussed just now. I'm sorry. Anyway, so now this is a new function, digital read. Before we use digital write, which basically writes this voltage to be 0 or 5 volts. Now digital read does basically the same thing, but instead of writing it, it reads the voltage. So if it's a plus 5 voltage, it will return this to be high, right? High is in logic high. And if it's a 0 voltage or ground, then this will be low. So that's all that digital read does. And the way this sensor is configured is that by default, it will output a high voltage. And when the moment it doesn't receive it back, like whenever it's receiving, whenever it's receiving the wave that it transmitted, it will give a high voltage. And whenever it stops receiving that, it will give a low voltage. And because of that, we want to actually check for low voltages, right? Because only when the wave isn't returned, like where did I explain? Yeah. So it doesn't get back the fully transmitted wave. So that's when it hits a black surface, right? So we we want the low voltages because that's when it has detected a black surface. So I wrote obstacle because it could be any surface. Like different surfaces have different properties. Based on that, it will change. But generally, like you check if the for like a line following robot, you'll say that yeah, we're on the line. That's what you'll do. And otherwise, you'll print that. Okay, serial dot print line is just like if you've used C before, it's just like a printf statement, or like if you use Python, it's a print statement. I'll get to exactly what the serial does in the next few slides. But right now, just assume that it's a print statement that you can visualize, right? And this delay is just so that you don't want to sample every single time. That gives you some form of unreliability. So usually you add a very small delay. So this is like 200 milliseconds. You probably won't notice it, but for robots, this could be a small, like a lengthy enough delay. But yeah, so this delay is just that. Anyway, next is the ultrasonic sensor. So the ultrasonic sensor, which is also known as the HCSR04, is the name of the component. But yeah, it's used to read the distance. So the IR sensor, you can only tell if like this surface is black and if this surface is white. You cannot tell how far you are from that surface or anything like that. All of that you take care by adjusting the sensitivity. So instead, you use the ultrasonic sensor when you want to measure distance. So what it does is it fires ultrasonic pulses and then it measures the time taken for the wave to return, right? And you use this to calculate the distance. So what it does is first it fires a sound pulse and then it the sound pulse propagates, it hits a object, it returns back, right? I think you guys would have studied echoes in class 11 or 12. So it's basically that the sound pulse is getting it's like getting rebounded from the object, which is assumed like a wall, and then it's coming back to the sensor, and you can measure the time delay between these sensors. So that's what the ultrasonic sensor will actually return. It won't return the distance. It will return the time taken for the wave that it sent to return back to itself. So coding this is a bit more interesting. Uh, so because of the way this works, we have a few pins. So there's a ground pin here, a 5 volt like VCC pin here. But there's a pin also called as trig and echo. So there are two new pins. So the trigger pin is what will allow us to trigger the pulse. So once you set the trigger to high, the ultrasonic sensor will start sending pulses, right? And then the echo pin is what will be receiving, and it will check if like the pulse that you send. So after some time, it will propagate like this. It will hit a wall, and then it will propagate back, right? So the echo pin is what will output high when it receives this wave back. So that's why we have two pins. One is to actually trigger sending the waves, and the other is to notice the echo from them, right? Uh, but there is one issue with the ultrasonic sensor. The sensor doesn't track the wave itself. It just knows when it sent it and it knows when it returned. It doesn't know what, like the wave that's returning, it doesn't know where it's from. It only assumes that it's from the wave that it generated. But let's say we have two sensors like this. So we have one ultrasonic sensor. Assume the box is an ultrasonic sensor. And we have another ultrasonic sensor here. And both are pointed towards each other. Then in that case, the sensor's wave from here can be input here. Like that can interfere with the wave here. And moreover, the echo can actually pick up this wave and assume that that's the wave that has returned. Like, how do I explain this? Let's try again. So this is the ultrasonic sensor, first one, second one. So this one, let's say it triggered and then it output a signal. But before that itself, this one has already been triggered and this signal is propagating. And let's say that the wall is somewhere here. So what will happen is that let's say that the blue color is one time instant. By the next time instant, the wave that this one has actually propagated is here. But the wave that this ultrasonic sensor has propagated has already reached this. And because of that, it assumes that this is the time delay between the signals. When in reality, the signal it sent has still not even reached the wall. So this is an issue that can happen with multiple ultrasonic sensors. But usually that's like, you can avoid that by, placing them on different sides or something like that. Anyway, um, so again, the circuit itself is very simple to wire. Both of these are digital pins. So the trigger is you are going to, so the trigger will be taking an input. Like it needs to be fed the voltage. So the trigger pin, you'll make that as an output pin. Whereas the other one, the echo pin, is what will be sending a signal. It will be giving us the results. So you want to make the echo pin as an input pin, right? So that's all. But both are digital, is the point. So the code for this is a lot more involved. So let's start with explaining the code. So the echo pin and the trigger pin. So if I erase this, you can see that the echo, if you follow the line, it goes to pin number 2. And the trigger, if you follow the line, it goes to pin number 3. So the echo and the trigger are defined here. Again, they're constants because we're not going to change them while we're running the program. Then there is this time delay, and then there's the distance. Okay, this is actually wrong. Um, this is supposed to be unsigned long. Okay, this can be long also, but let's say that this is unsigned long. Unsigned basically means that there isn't a signed bit. I don't know if you guys learned that in the last session, but in binary, there are different ways to represent numbers. One is unsigned, one is signed, and distance is supposed to be a float. The reason why distance is supposed to be a float, I'll tell you guys in some time. But yeah, this is a change I should have made. Anyway, so pin mode, like I said, you want the trigger to be an output because we are going to be writing a voltage through the trigger pin, and you want echo to be an input because echo is going to give us a signal that we want to read. And then again, okay, so serial. Serial is basically our way of communicating with the Arduino. So if you let me go back to Tinkercad, I guess. Um, so let's say here, let me quickly explain about the serial monitor. So I still won't go into how the serial monitor works as of yet, but I'll tell you what it does. So serial dot begin, and then there's a number here. This number is called the baud rate. What this number is, I'll tell you towards the end of the session. But serial dot begin basically initializes something we call as a serial communication between the two. What it basically does is that, when you're connecting the USB, you can also communicate with the Arduino while it's connected. So the serial is basically the wires within the USB that are being connected, and that will communicate with the microprocessor, and that will give us valuable data of what the microprocessor is doing. So for example, here I can do serial.write or println. So there's two main functions. There's serial.print and then there's serial.println. Serial.println will print whatever you're saying and then add a new line at the end. Print will just, like I said, it will print and then it won't add a new line. So it will continue in the same line. Anyway, so I will print blinked once, right? And then here also I can write serial.println started serial monitor. So one thing you guys will have to be careful of is the number you're entering here, known as a baud rate. You'll have to configure here as well as the serial monitor. So I'm going to start this, right? And here in the serial monitor, okay, in the Arduino you can configure it. Here I'm assuming it's already configured, but there will be an option to set the baud rate and you'll have to set it. But anyway, as you can see, uh, at the start, right? It printed started serial monitor, and then every time it reaches this line, it says blinked once. So this is our way of communicating with the Arduino, and this is very useful when it comes to debugging because you can print out the values of variables and other stuff. Anyway, um, let's get back. So that's like a very quick overview on what the serial monitor does. I'll come back to explain how it works later, toward the end of the session. Um, anyway, so yeah. Now, uh, yeah, my bad. Uh, yeah. So let me explain what this does. This basically just prints that, we're going to start measuring distance. This is a delay, does not need to be here, but we just added it, let's say. Now here, this is the main part. So first, you're setting the trigger pin to low. This is just a safety check. Make sure that it's not already high. Otherwise, it's going to get skewed. The data is going to get skewed. Now, delay microseconds is another delay function. The normal delay, this number is in milliseconds. This is in microseconds. So, a full magnitude smaller. So this will be 2 into 10 power minus 6 seconds. This is a very small time, but that's all it takes for the wave to get propagated. So now after this small delay, you trigger it high. The trigger pin is set to high. So now it will start blasting signals. And you wait for another 10 seconds to make sure that at least a few signals have been sent. And then you set the trigger pin back to low. Now the data is being sent. And after it's set to low, it stops sending. And then these signals just propagate until they hit a wall. Then there is this very important function called pulsin. So pulsin, basically what it does is it measures the time taken between this command and the time till echo pin is set to high, right? So till now echo pin is low, but then now it starts a timer. Internally it counts and then it will give the time in microseconds when echo pin is set to high. That's why before I was stressing on why this should be unsigned. Unsigned long integers can hold bigger numbers, so it will give a more accurate time delay. And the reason why distance is float is very simple. So you can see this calculation here, and you can tell two things about it. One is that it's the float. It will return a floating value because you're multiplying it with a floating number and you're dividing by 2. Now, what this number is the speed of sound in centimeter per second, right? So, um, yeah, so this is the speed of sound in centimeter per, I mean, it's not seconds, it's the proper units, but it's set so that whatever number you multiply this with, this will return the distance in centimeters, right? Um, and why you're dividing by 2 is also simple. So let's say once you propagate, it hits the wall, and then you have the signal has to travel the same distance back to return back to the signal, right? So you're actually measuring twice the time delay that is actually taken. So this is t. This will also take t, like to return from the wall back to the sensor. So you're measuring twice of the time you actually want, and that's why you divide by 2. The rest is just printing the distance. So like I said, this will this will not add a space like a new line after this, and so it will basically print distance and then the variable like what distance it's measuring and then the distance in centimeter. So while I get the Tinkercad setup, here is the attendance link and a small break. So if you guys have any questions, and yeah, you can ask it in the chat. Meanwhile, you can also fill the attendance form for this session. We started a bit late, so it will probably go on till 6:45, maybe a bit beyond that. But I'll try keep it before 7. We started only at 5:30, so I'll wait till like I think 6:20, maybe 6:22. 5 minutes I'll be. You guys can fill the form, and if you have any questions, you can ask in the chat. If I did go through anything too quickly or like something you guys didn't understand, let me know and I'll go through it again. So I did have a setup for showing you guys this working in real life. So I have a ultrasonic sensor setup, but right now I'm too scared to mess with the volume. So I will let it be for now. And toward the end of the session, I'll show you guys a working LCD and the ultrasonic sensor. So is there any questions? I'll wait for another 2 or 3 minutes for you guys to fill the form. And yeah, still, if you guys have any doubts, you can ask it in the chat, and I will respond. Oh, input pull-up slide. Okay. Yeah, yeah, okay. Oh, Pulsin, it returns in. Okay. Um. So Pulsin, it should I? Do you guys want me to change the slides? Yeah, yeah. So okay, let me clarify Pulsin quickly. Uh, I will. Okay, give me 2 minutes. If you have any more questions, put it in the chat. I will clarify that when I restart. Okay, I'm hoping most of you guys have taken attendance. I will switch the slide now. And in case you guys didn't take attendance, it's fine. Again, towards the end of the session, I think I will show it again if need be. Anyway, so one of you guys asked me about um, this constant and how it comes out to be. So Pulsin returns the time delay in microseconds. My bad, not milliseconds. This returns it in microseconds. So that will be 10 power minus 6 seconds, right? And if we take the speed of sound as 344 meters per second, so that will turn out to be, because you want to convert meter to centimeter first, that will be 344, like 34,400 centimeters per second, correct? But this is returning in microseconds. So if this is in microseconds, then we want this unit to be in centimeter per microsecond, right? And if you want to do that, you have to multiply this, because in 1 second it will transfer, like it will measure 34,400 centimeters, but in 1 microsecond it will measure 34,400 times 10 power minus 6 centimeter, right? So this is per microsecond. And if you do this math, it comes out to be 0.0344. So I'm hoping that clarifies the doubt about this. Another doubt I saw was the input pull up, right? So let me go to that slide. Yeah, okay. So let's say that this is a button, right? And let's say that let it not be connected to ground, let it be connected to some source or like some sensor, right? And we want to read this value only when this button is pressed, right? It sounds simple, but then when the button is actually not pressed, this is floating. So when it's floating, it will read um, random voltages, or we call it floating voltages. And this is bad because the Arduino or like your microcontroller doesn't know that the button is pushed up. Like you are controlling this button, okay? So the Arduino doesn't know that you've actually lifted the button. According to it, it's still getting values from a sensor. So rather what you would do is you would add this resistor and a 5 volt here. Basically what this does is when the button is pulled up, the 5 volt is what is connected to the input pin of the IC. Because there's nothing to drive it, so the current will be zero. So the voltage drop across this resistance will be zero, right? And let's say that this button is pressed, and let's say that the sensor gives 0 volts. Then in that case, what happens? One sec. So if this does give 0 volts, like it's shown here, then this is a direct short, right? Like it's directly connected to the input pin. So the IC will read whatever value is here, which just so happens to be 0 volts. And to make sure that there is not too much current flowing, this resistor is there so that the current goes like this, and it's a manageable current. It's not too much that will damage anything. Okay. I hope that explains the doubt that someone had about input pull-up. Okay. If you didn't understand it, again, at the end of the session, I'll again pause. So if you guys have any doubts, then I can explain it then. Anyway, this is a very small intro to debugging the Arduino. So that's a lot of stuff that can happen in a project, and these errors will, you can read the errors that the Arduino IDE gives you. Sometimes they might help, but sometimes they may not. So some memes I found about this. So this is something unironically that a lot of people do. You add a lot of printf statements, and sometimes it does magically work. That always happens. But do take this seriously. You add a lot of printf statements. It's in the official Arduino IDE community that you usually add a lot of serial print line statements to see what value is actually messing up. And this is a very simple meme, but it was something I found. Anyway, um, so debugging, the first example. So this one should be very simple. This is the code, and you can see that when I tried compiling it, it gave me this error. Expected a semicolon before the close brackets. So if you look at all the lines of code, there's a close bracket here and a close bracket here. Before the close bracket, this statement already has a semicolon. This statement does not. So this is the error, right? So it's a very simple error. But once you guys start coding, I don't know how many of you have experienced this before. I certainly have. A lot of times this happens. You will try find out the error and it will be a missing semicolon. Unironically, this will happen, and sometimes there are these weird compiler bugs that it says that the error is here in this line because it's missing a semicolon in like this line. It can happen. Stuff like this happens. Yeah. So anyway, next problem. So this is an example of a blinking LED code. So this code, its purpose is to blink an LED on pin number 9. But I'm not doing the digital write high-low directly. Instead, I'm doing this. This is a different logic that I've used. But if you actually run this circuit, the LED won't blink. In fact, it will always stay on. And but you can see that the code is actually compiled. So the compiler thinks there's nothing wrong with it, but your code is not doing what it's supposed to. It's not blinking the LED. So this is an example. I'm rushing through this because we're actually running a little bit out of time. But this is an example of what is called logical errors, right? And syntax errors the compiler can see, but logical errors compilers won't see, like this, right? Anyway, so in this code, what I'm trying to do is when the state is high, you write high, and when the state is low, you write low. But if you actually notice, the state is declared here and it's never being updated. So the actual way to implement this is shown here. This is the correct one. So this additional line is what makes this code works. Reason being, let's say first it's true, right? So the first time it's being executed, it's true, so it will be set to high. So first execution, it will be set to high. It will wait 1/10 of a second. And then when it comes back to this, state is basically not of state, right? This is what this line does. State is not of state. So state will be assigned whatever value it wasn't before. Before it was true. So now it will be false. So now the LED will be low. Then when it comes back again, before it was false. So now state will become true. So it will become high again. So, this is another way to write a blinking LED code, but this one, if you don't add this one line, it won't work. So this is a logical error, and these are much harder to spot. And yeah, so this one I've already covered. That's why I'm not going to stand on this for too long. But if you see, this is not what distance you expect to measure. Okay, for context, this code is basically the code that we wanted for the sensors, this ultrasonic sensor. You look at this code and then you look at the code I just showed you guys. Yeah, you look at this code, it's almost the same. Except now when you're measuring distance, you're getting some very bad answers and you're getting only integer values. This can be explained very easily by looking at this line. So this is another specific case of logical errors. The compiler didn't find a single issue with it because according to it, yeah, everything is fine. There's no syntax error. But if you look at this, pulse_in expects to return an unsigned long type. This, however, is an integer, right? So it's not having the capacity to hold the number that pulse_in returns. Okay, quickly, integers have a fixed capacity. Its capacity is 4 bytes. This is not required. I'll just tell it quickly. and this returns an unsigned long, which is more than 4 bytes. So when you put that data here, it causes what is called an overflow, and that is probably what happened here. Okay, I probably moved the wall a bit too far away, and that caused overflow and caused this number to be negative. Anyway, that's beyond the scope. I think that you guys might have learned in the digital systems class yesterday, but okay. But yeah, and then the second issue on why all of these are integers is very simple. We have defined this distance to be an integer. It's supposed to be a float. So that's why all of these issues, it was a number. It wasn't like a floating value that we want to see. Um, so again, towards the end of the session, I'll show you guys this working in real life. I'm a little bit scared to set up the camera right now after all the audio issues. At the end of the session, I'll see if I can set it up. Yeah. Anyway, so like I said, this is supposed to be an unsigned long, and this is supposed to be a float data type. Yeah, here I also wrote the time variable is measured in microseconds. So pulse and returns microseconds. Anyway, so now this is some new and interesting stuff. This is some of the basic communication protocols. So when we want to communicate between two devices, so we have our laptop here. So this will be our laptop, and we have an Arduino here, right? So this is an Arduino, let's say. How are we writing code here? Technically, the Arduino, all it can read is binary, and even your computer, all it can read is binary. Yet you're sending code over just like a few wires. Inside the USB, there's only 4 wires, like this extra data, but it's fine. There's like VCC, there's ground, and then there are two lines called data plus and then data minus. But is it not interesting that you're writing a full program worth of data? You're transferring that over just 2 wires, right? Before and all, when we were using 2 wires just to get two different values in the ultrasonic, we were using 2 wires just for 2 bits, basically. Like bit is either 1 or 0, right? So we were using 2 wires for 2 bits. And now we're writing thousands and thousands of bits over, I mean, it'll be even bytes or megabytes, but you're writing a lot of bits over just 2 wires, right? So how this works is through communication protocols. So I'm pretty sure you guys would have read about sequential circuits yesterday. So the basic idea is this. You sample, like instead of using 1 wire for a bit, in the same wire, you send data at set intervals. So there's something called as a clock pulse. So let me try draw a clock pulse. Clock pulse itself is very simple. A clock, like in our home, a clock ticks every 1 second, right? Instead, this has a fixed time period, which, like it will be in a lot of, like it will be in megahertz usually. Or sometimes even for processors, it's gigahertz. But you see that this will be a constant time, and this is very reproducible. That's all that a clock signal is. Anyway, so what we do is we send data. So this is a clock line. This is a clock. And you sample whatever is in a data line. So this is a data line. And you sample this data at fixed intervals, right? So if you do this, you will sample every time at something called a positive edge. A positive edge is basically when it goes from 0 to 1. When the clock grows from 0 to 1, that is called a positive edge, like right here. You represent it like this. But whenever you reach a positive edge on the clock, you will take a sample of the data line, right? So right now, if you take a sample, this will be 1. And the next time that happens, you take a sample, it's again 1. Next time that you take a sample, again it's 1. But then the fourth time it becomes 0. So like this, you can send data over just 2 wires, and you can send this data sequentially, and it's stored in stuff called registers. And then what happens after that is way beyond the scope of this session, but it's very interesting. And by like this is technically just a binary representation of a number, right? So this number, if you translate this is 2 plus 4 plus 8. So that will be, this is just you're transmitting 14. So you've just transmitted the number 14 between two devices over 2 wires. And when you're transmitting characters and stuff like that, you'll use something called as an ASCII number. So for A, it is 0x41. This is hexadecimal.
if you convert this, this will be 65. So A is assigned the number 65. So, but for this to happen, you both the sides need to know that you're receiving an ASCII number, right? So you send 65, it will receive 65, but it will interpret that, okay, I've received 65 in ASCII that represents A. So I've received A. That's what happens. Anyway, so that's basically what I've told right now. See, send each bit in fixed intervals, and you can basically this allows data transfer between two devices very efficiently. I will only be covering these three, but there are a lot more interesting ones like CAN, USART, and USB. I will be covering only UART, I2C, and SPI in this session. Okay, and each of these has their own pros and cons. So to start with UART. Okay, so if you expand this, this is universal. So this is universal asynchronous receive and transmit. So RNT is receive and transmit, but point being it's asynchronous, meaning there is no clock pulse. Instead, what happens is both the devices should be configured before send to sample at a specific rate. So instead of transmitting a clock signal, you are basically transmitting one is to transmit data like so okay. So T is for transmit and R is for receive. So the transmit of device 1 will be connected to the receive of device 2, and the transmit of device 2 will be in the receive of device 1. So this way, at the same time, you can transmit data. You can transmit data from device 1 to device 2, and you can transmit data from device 2 to device 1. This can happen simultaneously. And the reason why it's asynchronous is because the clock pulse isn't like, you're not sending it. It's supposed to be fixed. So before you're sending this data, both of these devices, they'll be told, okay, receive data at this fixed frequency. And that's why it's asynchronous. I'll tell you about this later, like what the synchronous ones are. But yeah, and the data itself is sent byte by byte. A byte is 8 bits. So every time you send 8 bits, okay? And then you send headers, right? So you send something called a parity bit, like a lot of stuff is there. Like if I go into this properly, it will take way too long. A parity bit, I'll just tell you, it's checking for errors in the data that is being sent. So in this 8 bytes, if there's an error, the parity bit will become high. There'll be also more information about what data is being sent, but that is for later. So that's all about UART. Okay. Now I2C. I2C, okay, so this is another communication protocol, but rather than using, one wire for transmitting from one device to another and the other wire for transmitting, like, rather than using this configuration, you use a configuration like this, where there's something called a master and there's something called a slave. Right now, I'm not going to tell what those are. I mean, see, master, it gives like the slight misconvention that, only this form of data can happen. Like only from master to slave data communication can happen. That's not true. You can transmit from slave to master also. The reason why we decide master and slave is because this is what gives the clock signal. So before the issue was you can transmit only at one fixed frequency, right? Now, let's say you want to transmit at different frequencies at the same time, right? Not at the same time, as in first you want to transmit data at, I don't know, 16 megahertz. And then after that, you want to transmit data at 4 megahertz, right? Different like readings you're getting at different times, so you're transmitting at different rates. So to do that, you control the clock and then you set the data bits accordingly. So this is what I explained in the first slide, right? So there will be one line for setting the clock and then one line for data. This is basically what I2C does. And now you might ask, like, before there were only two devices, you know that if you are sending from TX bit, you know that it's going to device 2. But when you have a configuration like this, all of these are connected to the same clock and the same data lines. How do you know if I send data from here, how do I know which one will be receiving the data? So to take care of that, there is something called an address. So I don't know if I wrote about that here. Yeah. So there's something called an address. So each of these devices is like when you're writing code for these devices, you will say that, okay, this is my address. let's say that this address is 0, or let's say that, wait, let's say that this address is 2, this master's address is 4, this address is 6, and this address is 1. Okay. So when you're transmitting data, before you send the actual data, you will send the address. So before you send, let's say that this is the data that you're transmitting, like 0 1 1 1 0 0, you will send a 7-bit address. 7-bit is very arbitrary. Don't worry about that now. But you will send the address of where this data is supposed to be received. So if I set the data like this address to be like this, which by the way is 2 in binary, right? So if I set 2 in binary to the address, then the data will be read only by this. So in the protocol, every device checks if the address matches its built-in address, and if it doesn't, it doesn't receive that address. It doesn't receive that data, right? Anyway, sorry for that. But yeah, and similarly, if I want to send data to this slave, then I will write 6, which is 0, like 1 1 0. But yeah, that's basically how this works, how I2C works. But you can notice one downside. See, one upside we gain, that is like a pro of using I2C, is you have only 2 wires for communicating between multiple devices. You can have like many devices here. This I put only 4, but you can have a lot more. If you're going to do the same thing with UART, like let's say you have a third device here, right? And you want to communicate between all of them. You'll need 2 wires here and 2 more wires here. So for just 3 device communication using UART between all the 3, you will need 6 wires, right? And if you make it fourth device, that will be another 2 wires here, another 2 there, and then another 2 there. So that will become 12 wires. So as the number of uh, devices increase, the number of wires you need increases exponentially. So that's why I2C is very nice, because it keeps it tidy and it keeps only 2 wires, right? Wait, till this, any question? I feel like I've sped through this a bit. Any question? If you guys have any questions, enter it in the chat. Oh, okay. I2C full form is integrated circuit. It's like it's fine. Other than that, there's like SDA and SCL, which is serial data and then serial clock. Like point being, the name doesn't matter. SCL is what is going to transmit the clock. Wait, let me show. So SCL, this is what will be sending the clock signal. The CL is for clock, and here the D is for data. So this will be sending like the data bits, right? But yeah, and then I2C, I don't know why it's named like that, but yeah, it's integrated circuit. Where exactly are communication protocols used? Um, that is a good question. So let's say you have like a complex robot, right? Most complex robots will have like you'll have multiple dev boards itself. Like you'll have an Arduino purely for like motor control, and then you'll have a Raspberry Pi. So you want to communicate data between these 2 devices, you'll use stuff like this. And moreover, if you go into some more complicated sensors, they will also use like these protocols to communicate. So I don't want to get too deep into this, but there are stuff like barometers, and there's stuff like my voice is breaking. I have no idea why. Is it better now? Okay, fine. If it's good now, then fine. But yeah, there's stuff like barometers, and there's other like internal IMUs, we call it internal measurement units or whatever. But those all communicate data via these protocols. So knowing these protocols will be very good, because yeah, you'll use it to not only interface with sensors, but if you have like a lot of development boards together, then you'll have to interface, like you'll have to communicate between them, probably using one of these. Okay. Um, Anyway, so there is a downside to I2C, and that is that there's only one channel for data transfer, right? Like the same upside is the downside. you have only one data line. So if you want to communicate at the same time between like two different devices, that's not possible. Like in UART, you can communicate simultaneously between the two devices. But in I2C, that's not possible because when one device is using the data line, that data line is occupied. You cannot, like, if this master is sending data to this slave, at the same time, not only like can the reverse not happen, two other devices also can't communicate with each other because this data line is now used, right? So these like it slows down the speed a lot and like you can't communicate simultaneously. Um, so to fix that, there's something called SPI. This is it's like much faster, let's say, than I2C. So let's say one thing is the protocol wastes time sending the address. Like I told before, you send address, like you send the data, you send the addresses. So that actually is a waste of time because you're sending 7 bits for no reason, right? So to take care of that, you have something called slave select, right? So this slave select will basically decide what slave actually gets the data, right? Sorry. Anyway, and then there are the other thing is that it doesn't allow for parallel communication. Okay, so here there are two lines. There is MOSI and then MISO. So MOSI is master out slave in. So output from the master to the slave, right? That's MOSI. So from the master, you're going to slave, and then that's MISO. So from the slave, you're going to the master. So now, like a master and a slave can communicate parallelly. So that is one benefit. And then the clock line is there again. We don't want asynchronous because then we can't change the data rate as we're running it. So we use a clock line between all of these, right? So I don't think I'm going too much over SPI. It is a little bit more complicated than this, but yeah. Let me just go through these alone though. So in the slave select, if you send a high voltage, then like if you set like let's say you want to communicate with this slave, then you set SS1 alone to high and these two to low. In which case only this slave will receive the data. And here you're using two lanes of data transfer, so you're allowing back and forth communication. So the master can communicate with the slave. Parallelly, the slave can also communicate with the master. So here again, the wires is a lot more than I2C, right? So here you can see again four configuration, like four things want to communicate. Yet the number of wires is what? 1, 2, 3, 4, 5, 6. That's 6 wires. But at least out of the master. But here it's only two. So it's more wires, but still better than UART, right? So for UART, I think it was 12 wires, right? That we calculated. So it's still better than UART. And yeah, that's all I'm going to do about SPI for now. There's a lot more to it. If you guys are interested, read about it. It's a very interesting protocol. But that's about it for now. And before we go on to using the LCD, a quick note on serial monitors. So, like I said before, these two pins are special in a way that they allow for UART communication. And the thing is, how does serial actually communicate? Like USB protocol is different from UART, and the chip itself can only communicate in UART. So that's where this chip here comes into play. This is like I forgot the name of this, but it's used to convert the serial data into data of a format that UART can use, and the reverse is also true. So it allows for um, data from the Arduino to communicate with this and then converts it to a form that can be sent to the USB. So this small chip is technically what allows the serial monitor to operate. Okay, and the baud rate that I was like avoiding before. So like I said, all of this technically operates on UART. Like the serial monitor is just UART technically, and so the baud rate is the transfer speed. You remember how I said UART doesn't have a clock line? This is why you have to configure both devices to use the same data speed beforehand. And that is what the baud rate is. It's in a unit called bits per second, but that will basically determine how fast you're sending data back and forth. And yeah, so the first device here in our analogy, the first device will be the Arduino, And then the second device will be the serial monitor. Let me clear this. So this is the Arduino Uno, and this will be our serial monitor. So I will show you guys after this, towards the end, on how to use or like how to set the baud rate in serial monitor. That will be a nice box. I will show that later. Anyway, so that's a quick note about this. Yeah, so the baud rate is basically the frequency at which you're sending data to and from, like to and fro from the Arduino and then to the computer and so on. Anyway, that's about the basics of communication protocols. I feel like I rushed it. Any questions? Any questions? If so, send it in the chat. If there are any questions, let me know. I will try wind up in the next 15-20 minutes. Will we have that demo? Can you be a bit more specific? What demo do you refer to? Um, as in the LCD and the ultrasonic sensor working? That I will do after this session. So this is the last section. I will go through this somewhat quickly. Yeah, I will do that soon. Okay, so if there's no other questions, I'll get started with this. So till now, we have no visual output from the Arduino. Say that you have like a robot or like a car or something that you've made, and the Arduino is here in the car, but you don't want to connect your laptop to it to see what values it's reading, right? So rather, you'll have something like a LCD here, and you'll use this LCD to display some of the data, like the speed at which it's going and stuff like that. It's just a cool add-on, but it can be used in some very nice use cases as well. So this is having a lot of pins, right? So there are 8 data pins. There is an LED plus and minus pin. There is also a separate VSS and VCC, so that's another ground and 5 volts. There is a contrast control, and there's a register select, read, write, enable. So I'll tell you this quickly. All of these are used to program the LCD. So the LCD has a set of commands that you can send it via the register select, read, write, enable, and these data pins. And that programming is actually very difficult, and you'll have to read the full data sheet. Um, but luckily, there are people online who make libraries. So we will write a single line, but in the backend, a lot of processing will be done, and the LCD will be fed the data so that it prints whatever we want it to print. Anyway, so so yeah, like I said, it is possible to program the LCD without an MCU, which is how you read the data sheet, you know every command, but you need, but like now we'll just use external libraries because doing this, programming it without the MCU is slightly beyond the scope of this session right now. So now notice that we have so many pins here. Connecting this to an Arduino will basically take up most of the pins of the Arduino for this LCD itself. Rather, we use a communication, not a communication interface, let's say. This board is an I2C board. So what it does is it gets data in the form of I2C, and then it converts that to data that it converts that to data of these pins so that it can read it, right? So this is basically something that goes on the back of the LCD, and then you can send data via the I2C protocol, and it will read it. So like I think someone was asking, right, where will we use this? So, this is a very beginner friendly use case. Here we'll be using I2C simply to communicate with the LCD. So instead of using, I don't know, I think it was 12 wires, yeah, to only 4 wires. So, it's a good save. I think it's more than 12 wires actually. So they're saving a lot of space on the Arduino. So to actually install the library, Okay, again, I will show this demo, I think at the end, which is like in like 5-10 minutes. So there's something called a library manager, which is this icon. It will be on the left-hand side of the Arduino. You go there, um, and then you type in liquid crystal I2C in this search box. And then this one by Martin, whatever this is, I can't read it. And then you click install. So this will set up or install the liquid crystal I2C library in your computer. So after that, there are a few commands that we use. So the first one is the liquid crystal I2C. Like this basically defines that it tells the compiler that okay, there is an LCD. This is an address. Okay, so you know how I was telling I2C requires an address? So this module has an address. And to communicate with it, we need its address. So there are programs online. I'm not going to show that now. But for mine, it was 0x27. And for most of them, I think it's 0x27. Or it might be 0x33. You'll have to run a program and check. But yeah, so you'll use a communication, like you'll use a address, sorry, and then you'll use this is the size of the LCD. So the LCD itself has a grid kind of pattern. It has 16 columns and it has two rows. So there's 16 columns and then there is two rows. So that's the data that we're entering here, right? And yeah, that's the data we're entering here. And then the address, yeah, again, it changes based on the I2C. LCD.backlight. So I can't go through how the LCD functions because of the time constraint. But the LCD functions, for the LCD to function, you need something called a backlight. And to enable this backlight, there's this command called lcd.backlight, which turns it on. lcd.init is something you generally run at the start of the program to tell it to basically clear the display of whatever was there previously. It resets the cursor and it also does a few other things, which I'm not going to mention. So after this, we use a set cursor. So if you have a grid like this, right? I'm going to draw a smaller grid. Yeah, so this is a 4x2 grid, right? So each of these have a position, an XY coordinate basically. This is 0, 0. Like in programming, you usually always start with 0. This is 0, 1. It's row, column, by the way. 0, 2, 0, 3, and then this will be 1, 0, and so on. And then this will be 1, 3. Yeah. So basically, you can set the cursor to a position. For this example, I set it to 0, 0. And then you use lcd.print text, right? So the text I sent was hello, smiley face. So that is the text that it prints. So that's all that it does. Again, the code for this, like I said, so the code for doing this example is this. You define the I2C. Before that, you have to import these two modules. This module is what actually does the I2C communication. It was used, I think, to get the address. It might be required for this example as well. lcd.init, so it clears everything, makes sure the backlight is on. This you don't really need. I just added it. It's serial is generally something you use very commonly. Then lcd.clear. So it clears, okay, this function basically clears whatever was there before. I know init does it already, but these two are helper functions you almost always use. Then you set the cursor to 0, 0, and then you print this text, right? So another way to make it more interactive. So this will be the session, I mean the demo I'll show later or like in 2 minutes. So you use something called lcd.write, right? So lcd.write, it basically prints one character at a time. lcd.print prints all of these at a time. lcd.write will do exactly one character print and it moves the cursor to the right. So this code, I'll walk through what it does and then I'll show what it does as well. So this code, it turns the LCD on, turns on the backlight, begins serial. So for this example, serial communication is actually needed. Now, this command basically checks if the serial is available. Sometimes you won't actually, you might have configured it wrong so that the serial monitor is actually not available. So this simply checks if the serial monitor is available. Then this is a small delay we add. We clear everything. And while it's available, you print whatever the serial has read. Okay. So whatever the serial as the serial dot read, like if you enter, let's say hi, okay, so it will read it and then it will print one by one. So it will first read H, it will read H and then it will write H, then it will read I, then it will write I, and as it will show you, when you press enter, this doesn't know that enter isn't like a printable character. So it will actually go and try write the escape sequence, which is printed like this. Now I will try, so while I get this set up, if anyone missed the attendance, you guys can scan it quickly. Um, Meanwhile, let me try get the camera set up. Yeah. So is my voice still clear?
For anyone who wants to stay for the demo. I hope you guys are able to see this. Right? I will try run this. Hopefully my voice isn't breaking. But yeah, I'll try set it up so that you guys can see. Yeah. Okay. So this is not required, but when you're on Linux, there will be this slight issue where you guys will have to manually add read and write permissions for the USB itself, but once you do that, it should be fine. Okay, so I hope you guys can see this. So currently it's reading a distance. I will try show you guys my wall, I guess. So my phone, if you can see it in the camera, is my wall, and you can see that the distance drops to around 5.4 or something. It keeps on oscillating. So that's another issue with the ultrasonic sensor. You can see that it's actually oscillating the reading. The reading doesn't stay constant. It could also be that, you know, the wall that is my phone is moving, but yeah, that's an issue. Anyway, let me move my phone back and you can slowly see the value increase. So it's 8, 9, and yeah, now it's 14. So it's back to just measuring the wall. So this is one example of the ultrasonic sensor working. You can see, like, I suggest you guys go and then try do this on Tinkercad again. On Tinkercad it won't be as easy to see. Like, you will actually set the value there, and here it's much easier to see, right? Wait 1 second. Can you guys hear me? If my audio was bad for the last 5 minutes, please let me know. I'm going to assume that somehow the audio was fine, and I will continue. So I'll try show um, how the LCD works. In case the audio wasn't fine, it's fine. I'll take another 5 minutes and I'll show you guys how the normal I2C one, ultrasonic culture works. So let me connect. Okay, so this is going to be quite hard to see. I will probably have to move the camera around a lot, but okay. So let me clear the output. Yeah, by the way, this was the baud rate that I was telling you about. So in the serial monitor, the button to open it is up here. Once you enter that, there will be a baud rate here. So you'll have to set this. You'll have to set this to whatever you set here. So in serial.begin I set 9600. That's why I'm setting 9600 here as well. Anyway, I will try enter hello, right? And I will try show you guys what is actually being shown here. So hopefully you guys can see it. The last character is what I was saying. It is the escape character. So in ASCII, every character has a number. The escape character also has a number, and it's trying to print the escape character itself, which is why it's just trying to print lines. Anyway, now I'll send something else like hi, and you can see that it gets updated. So this is what I meant by, oh sorry, this is the wrong code. This goes back to me showing that once you flash something, it stays flashed. So as you can see, yeah. So hello. As you can see, this has been updated to hello, and yeah. So that is the LCD working. Hopefully that was fun. If you guys have any more questions, then yeah, feel free to ask me. I'll answer them. But yeah, that was the session, guys. Thank you for attending. Any more questions you can ask? I think one of you asked a question: how Arduino is able to communicate via I2C? Isn't it support UART? Okay, so Arduino supports UART and I2C. I mentioned it beforehand. One second, let me remove the camera. Yeah, so the Arduino supports a few modes of communication. I have not used SPI with the Arduino personally, but it definitely supports I2C and UART, because let me go to that slide. So these two are the ones that support UART. These two are technically dedicated or like the default assigned value for I2C communication, but any of these pins can be configured to use I2C. So let me make this clear. UART, like the microcontroller is programmed to take UART as like the form of communication by default. However, you can like program pins so that it communicates via I2C. I2C itself is just a protocol. Everything else is a bunch of wires. As long as you can send clock pulses with the correct frequency and data data pulses with the correct properly, any two digital wires can be used as I2C. I2C itself is a protocol. When I said the Arduino communicates via UART, internally it's programmed so that it accepts UART as a form of communication. So whenever I'm using the serial monitor, I am forced to use UART. However, it doesn't mean that I can't use any other two pins as UART. So if I can use these two pins and I can connect it to another device, and somehow these two have the capability to transfer data at the correct rates, then these two can also be used as UART. So I hope that clears that doubt. Any other question? So any other question you guys would have had? Otherwise you can end the session. If there are no more questions, then I will end the session. Yeah. Um, yeah, I'm gonna assume no more questions. So